Swayam Prabha. Digital India. Educated India.
Welcome to the course of Design Practice for Intelligent Product Design, and in these we have already talked about how to generate design concepts. We have taught two different techniques to you. One is the axiomatic design and another is the trees, which is theory of inventive problem solving. Now, if I assume that you can generate a new concept, the challenge now that will come to you is that how to implement that concept, because this course is going to enable you, as I told you, starting from the concept till the development of the concept in terms of an intelligent product. In that direction, the first step that you now need to take after selecting a concept is how to productize this concept, which means how to select material, a material or a series of materials in order to generate the embodiment of the product. That is what will be our focus in next few lectures. So, I have named it as material selection in mechanical design. Material is the first part of any mechanical design. Unless you choose a proper material, it is going to be either very expensive, the product, so that people would not be able to purchase it, or if you go for a very cheap but short lived material, maybe it will not be, the lifetime of the product will be so low that people will not be happy, the customer review will not be good. So, hence there is a proper choice that you have to make in this direction. Now, we need this for mechanical design first, because later on we also have to carry out an electrical system design in terms of sensors, actuators, microprocessors. I will come to it later on, but our first focus is mechanical design. So, what is this mechanical design for which I have to choose the material? Of course, mechanical design refers to the mechanical components of a system that have to carry some mass, and that have to carry some loads. In other words, it should be able to sustain some loads and maybe additional functionalities like say some thermal requirement, some electromagnetic requirement, and also at the end do not forget that it has to be manufactured. Okay. The design now has to give birth to a complete product, you cannot keep it as a concept. So, at this stage our design will refer to the selection of engineering materials based on a set of defined properties. What are these properties? I will come to it in a minute. Now, think of the significance of this particular concept that we are talking about. That you think of it that in the concept generation phase, you have come up with a new design of a water bottle. That is what we were thinking of any product, let us say it is this water bottle itself, and you have come up with a concept. But now, in this concept for embodiment, you have to think of it that what will be the mass of this system, and that would mean that there will be two type of contributions of mass. What we always say is that the dead weight of the system, dead weight or the structural mass, that is the mass of the empty bottle, structural mass plus the payload. Payload, typically we have borrowed the term from the aerospace industry, means that how much of additional load in addition to its cell weight the system will be able to take. Now, these actually vary from the context to context. For example, if I am developing something on the earth, then there is a gravitational pull. So, the load is something. If I am developing something underwater, an underwater vehicle, because of hydrostatic pressure, there will be the effect of self weight will be less, but there will be the other type of forces that will come, like a compressive force that will come on the system. If I do something which is space borne or airborne, the space borne part, first of all, if you think of it, there the effect of gravity would come down, it would become very, very small. So, that the self weight will be less. On the other hand, there can be other problems because of the lack of environment. I will come to that point also. So, the first decision we have to think of it is that, well, the system should be having some mass, but how much of mass, and that is predominantly determined by what is the payload for which it is designed. Like if I consider this water bottle, then the payload is whatever is this 100 milliliter or 200 milliliter of water, then the weight of the water is the payload it has to carry. So, that it can carry this weight, what should be the minimum thickness of this bottle, that is important from this point of view. But there will be again many other possibilities of loading, because a bottle may not just simply remain as a simple bottle, as I told you that generally these sorts of things are packaged in a long stack. So, the weight of the stack also comes on the system. So, what should be that stack size, that will be an additional force in addition to the payload that it is going to carry. So, dead weight which is having structural mass plus payload, and then we have to think of the environmental condition which is going to give me additional forces, okay, that can give me the additional forces. And based on all these things, the embodiment has to happen. Now, this additional force may not be only mechanical in nature, additional force may have other type of requirements. For example, like this particular bottle is holding water. So, one additional requirement should be that the water should not spill out. So, which means the permeability of the bottle material should be, the porousness should be so low that the water molecule cannot escape. You cannot have a paper bottle to hold the same thing. So, this is an important consideration. Now, suppose it is not water, but suppose it is Coke. In that case, it is going to have not only H2O, but a very small diluted amount of carbonic acid in it. So, it has to be corrosion proof also, and suppose it is to be kept cold. So, then in addition to the chemical corrosion protection that you have to think of for the embodiment, you have to also think of that how to take care of the problem of the temperature. That means, whether it should be thermally insulating in nature, and also what would be the thermal stress that will be coming into the system. So, you need to design the whole system keeping all these points in mind. These are the essence of mechanical design. In this direction, I will gradually explain over the courses of lecture. The major considerations can be classified into 6 groups. The first problem is of course the price and the availability. The material should be cheap and the material should be available in the locality. So, that is the first important point. The second point is actually a whole series of mechanical properties that we have to be aware of, and I have only given some representative properties. There are actually many more than these, but these are certain fundamental mechanical properties that you have to be aware of. The first of course is density, which we all know, that is the mass per unit volume. Then the modulus of elasticity. Modulus actually controls the deformation of the system. That means, if the system is having low modulus of elasticity like polymer, then I would be able to deform it. See, so easily I am able to deform it, because it has a low modulus of elasticity. The same force, if I apply for this pen, I won't be able to deform it, you won't be able to see. It will deform, but it will deform in a microscopic scale. So, it will be having a higher modulus of elasticity. Maybe the difference is that this would be made of, let us say, low density polyethylene, and this will be made of a high density polyethylene. So, the modulus of elasticity would change. Damping is another very important property. Damping is related to the noise and vibration. So, if we design a system, we always try to see, unless it is a musical system, it should not vibrate. So, it should be, you should be able to absorb the vibration in the system, and that property is the vibration absorption property is controlled by damping. Then there is yield strength, and two strength we have talked here. One is the yield strength and another is the tensile strength. Of course, tensile strength you know is specifically guided towards the tensile force resistance of a material, and the yield strength, that yield strength actually talks about the point beyond which you will get irrecoverable deformation in the system, which we also say plastic deformation. So, we do not want to go beyond these points. And in terms of the tensile strength, this would create the tensile failure in the system. Now, every system need not always fail by tension, but generally materials are weaker in tension and generally they are better in compression. So, compressive strength is also important, and I told you only basic minimum I have kept here, which are almost every time required for a design. Hardness is another very important point, because if the hardness is not proper, then you are always going to get scratches. So, this is something that actually sort of controls the resistance towards the plastic deformation, okay? Resistance to plastic deformation. Fracture toughness. If I drop something and if it breaks, then if it breaks very easily, that means it cannot take the impact, then we say it has a low fracture toughness. So, fracture toughness is something to do with the brittleness of the system, that how brittle the system is, and generally we try to design a system which is much less brittle. Then there comes fatigue. Day in and day out, if you subject a system to repetitive load, then there is a kind of a weakness, the cracks develop in the system, and as a result sometimes you may get a sudden failure out of it. Many of you might have tried this simple thing, that if you take ductile, apparently ductile copper wire and you repeatedly twist it, or deform it, bend it, okay, up and down and up and down. After a few cycles, you just press a little bit of load, you will see there is no ductile failure, it is just like a brittle material, it will snatch out. So, that we always try to avoid. So, wherever there is a dynamic loading, the fatigue becomes very important. So, this is against the dynamic loading. And similar to the mechanical fatigue, you can also have a temperature variation that will create the thermal fatigue resistance. And finally, the creep is also a good important property that we need to have, particularly when a material is subjected to a force for a very long time. So, this is also deformation, but the difference between that property of modulus of elasticity and this is that it is deformation under constant load. Of course, then we have other properties like thermal properties, like optical properties, magnetic and electrical properties of the material. And then we come to the group of oxidation, corrosion, friction, abrasion and wear. These are important in terms of the surface behavior of the material. And then we choose also a material from the ease of manufacturing point of view. Some materials are difficult for machining, like if you choose titanium, titanium is difficult to machine. So, ease of manufacturing is a very important issue, and the same thing is true from the joining point of view. And finally, last but not the least is how the material appear, the appearance, the luster. That is why we go for gold or we go for jewelries, the appearance, the texture, the feel of the material. This is also important in terms of designing a product. So, these 6 set of properties we always look for in a material, and you need not get all the 6 properties as good as you wish. There you have to do some sort of a compromise. Now, there is a long evolution of materials. People today have many choices. The point to impress you is that if I suddenly take your clock back to 10,000 before Christ, then your material selection would have been much simpler, because you would have things like wood, skin, fiber, some fiber, stone, flint, pottery, glass, that is it. That would have been your glossary of materials. Later, of course, people added to that bronze, iron, etc. So, that you became much more conversant in terms of using new materials. Then the metals came in a big way, cast iron, steel, alloy steels, etc., which kept us occupied till almost the beginning of the last century. And then there came suddenly a big development of all the super alloys, which we will see gradually in this course, which you can use, and also a new type of materials called polymers and elastomers. So, not just the metals, and again a composite group and ceramics and glasses. So, now today naturally we have so many materials that there exists of course the point that which one to choose. If you have too few, you do not have that problem. If you have too many, then you have to know which one to choose and why. In order to go through that full story, always keep the design process back in your mind, and that design process, please keep in your mind, starts always from the need of the market. If the market needs a luxurious product where cost is no bar, then you can go for a super alloy. If the market is looking for something which is for the bottom of the pyramid design, it has to be affordable, then of course, you have to choose a material which will give you a reasonably good life as well as it is cheap. So, market need defines the selection of the material, and from there we have done the concept generation, and now we are somewhere here where just before the embodiment we are actually coming here in terms of the material selection process. And for us right now all material is kind of okay, but at the end of these few lectures, from that we will create a subset of materials. That is the goal of next few lectures. And then once we do the embodiment design, we will not even have a subset of material, but we will design with only one material. That will be the detailing phase and the product phase, so which is going to come up. Now, I told you that we have an enormous options, level of options today. All these options can be grouped primarily into 4 groups of materials. The first group, where you need something which is heavy and strong, metals and alloys are the best, and there are so many variations: iron and steels, aluminum alloys, copper alloys, nickel alloys, titanium alloys. These are the major alloys. There are also some other alloys there like zinc alloys for example, but they are not so major. So, these are the major alloys that are used for product design. Then there is the polymers, large group of polymers like polyethylene, polymethyl methacrylate, nylon, polystyrene, polyurethane, PVC, rubber, polyether ketone and polyether ether ketone. So, there is a large group of polymers. And then ceramics. Ceramics are something which are, we should say, technical ceramics, because ceramics are there with us for a very long time. You think of those kulhar which we use for chai, that is also ceramics. But today the ceramics we are talking about are actually very high temperature and very special grade of ceramics like alumina, magnesia, silica, silicon carbide, zirconia, cement, etc. And finally, there is composite. Almost all the aircrafts, particularly where weight is of a considerable important part of the design, that the system should be as light as possible, composite plays a very big role. So, all the aircrafts, all the missiles, you will see this type of composites: carbon fiber reinforced plastic, glass fiber reinforced plastic, carbon reinforced composite, etc. So, we have a large kitty of materials with us. To make our life more challenging, we have some advanced and exotic materials also, like we have the smart materials with us. There are 4 groups of smart materials. They are 4D materials, means they change their nature with respect to time. You can change it, like piezoelectric material, which can generate an electric charge in response to a mechanical deformation. Magnetostrictive material, the same change, similar change can happen, but with a change of magnetic field in this case. Phase transition dependent material, which remembers its original shape, and in this case it is temperature or so to say heat initiated change, and in some cases it can be magnetic field also. So, we call it, some of them we call it as a shape memory material. Then we have these electromagnetorheological materials, in which the viscosity changes, change in viscosity in response to electric and magnetic field. So, this is a large group of exotic material which is available in addition to those 6 group of materials. There is a group of biomaterials also that is coming up in a very rapid way, and there are so many biomedical applications. Prosthetics is going to be a group of intelligent systems very soon. So, all your prosthetic leg can carry yourself today. So, this type of systems would come up. So, biomedical applications would include joint replacement, bone plate, bone cement, artificial ligament, heart valves, some of the great applications, stents, cochlear replacements, okay, and then of course, contact lens, surgical sutures and all sorts of things. Now, in this case, the materials that are slightly different from whatever we have earlier considered, a new group of alloys like cobalt chromium alloys, stainless steel, titanium alloys, vitalia, another very interesting alloy, and amalgams, which is made of mercury, silver and stannum. Shape memory alloys, of course, I have talked about both binary type or tertiary type, and they are used in so many intelligent applications. As I told you, starting from the joining in terms of implants, so many types of implants, and then the heart valve itself, and then the amalgam for the teeth. There are plenty of applications of such materials. Polymers also are coming in a big way, like the silicones, special group of polymers, polyethylene of ultra high polyethylene, UHMWP, and then PMMA, and they are used in orthopedics, artificial tendons and facial and soft tissue reconstruction in so many ways. One good part of polymers is that they can be 3D printed very easily. So, you can design such products very easily. Ceramics are also available as biomaterials, particularly ceramics like alumina, calcium phosphate, synthetic hydroxyapatite and pyrrolic carbons, etc. Another group of material that is becoming very popular are the aerogels. Aerogel is a material which is about 90 to 98% porous. So, they are very thin, and they, because of the porosity, they are also good insulators. So, you can actually use these materials to create a thermal barrier or thermal insulation. Also, because of the porosity, they are good acoustic insulators. So, aerogel is again another group of advanced materials for us. And finally, the carbon nanotubes, which is discovered in 91, but today there are revolutions in terms of the applications of carbon nanotube and graphines, and these are basically some new allotropies of carbon atoms other than what we generally know, but we take the advantage of the covalent bond. That is why they have a great modulus of elasticity, and it is about 100 times stronger than steel. Only thing, it is expensive, the cost becomes a factor, but it has very high thermal conductivity, 10 times of copper, and also high electrical conductivity, which is 100 times of copper. Now, if I include carbon nanotube in some kind of a polymer, I get something which is a CNT based composites, which will be both extremely lightweight as well as functional in nature. So, we can make good use of such systems. So, with this little bit of background, we come to the material selection process. So, the important points here are the mechanical design, the design flow chart, the doubling time, the resource availability, eco efficiency and HP chart. One by one, we will go through all of them. And I have already given you the basics of this design, so I will not repeat it. The flow chart also I have talked about it, that what comes under the concept part, particularly the detailing is here, that determination of the function structure, seeking the working principles, evaluation and selection of concepts, and what comes under the embodiment part, that is also detailed here, and the detailed design part of it. So, otherwise I have already talked about this system to you. Selection properties I have just now touched. Now, come to the very important part of selection properties, which is the price and availability. Price is very important, and that is why the price we have kept here in terms of relative price. Let us say if I consider approximate price of mild steel in terms of 100 units, then where are we in terms of platinum, which will be 12 million times of mild steel, or diamond 10 million, or gold 9.6 million. That means, they are so much expensive in comparison to the mild steel. Possibly CFRP, which will come out as 20,000, is the first good one. So, if you consider steel as 100, CFRP will be 20,000. So, you know that it is in terms of price, it is 20,000 by 100. So, it is about 200 times more expensive, but still it is okay if you consider the benefit that you will get out of the system. And then you go through the long list, but I think the next important one for us is the titanium as a material, and this will be 2000. So, if I compare with respect to steel, then this is 20 times more expensive than steel. Just you have to have these figures always in your mind. If in comparison to that, I go for something like nylon or a polymer, it is 1500 to 1000. So, let us see where we are for nylon, and that tells us it is about 15 times more expensive, but this is a special grade of nylon, nylon 66. Come down now and come to GFRP, glass fiber reinforced plastic, that is about 1000 units and divided by the steel as 100, you know that GFRP is 10 times more expensive. And then I come down in this list more and more, I will see the plastics coming up here, and they are actually as cheap as the steel, though not so very cheap, but as cheap as the steel. And this list continues here and gives us kind of an approximate idea of the relative prices. So, this is important for us as engineer, we must keep the cost of the material with us. Now, what about the abundance of the material? Well, in terms of the basic elements, you can see that some of the materials are not so abundant in the crust. For example, titanium not so abundant in the crust. So, their availability is generally questionable. Similarly, if in the ocean and in the atmosphere, you can again check the abundance of the material. And from the abundance point of view, iron and aluminum and of course, silicon, they are good structural materials which are very much abundant. So, these materials are abundant, which means these are sustainable also. If I use these materials, it will be great in terms of design of the system. Now, we always should keep this McKelvey diagram with us, which talks about two things. What is the current reserve, that is the known deposits which can be profitably extracted, and what is the resource base. And keeping this point in mind, you can see that this is where is the reserve, which is always smaller, and there will be always possibilities of undiscovered ore, but the more you go towards that direction, maybe it will become not economic, and that is why reserve is always lesser than the resource. And we have to choose our material keeping the reserve in mind, not the resource potential, because it may not be commercially feasible to extract, because for each and every material there is an energy that is required consumed to extract it, and you can see that that comes down sharply as I come down in this link. So, accordingly I can think of the material for us. Another important point here is the doubling time. That means, what is the trending material, that is period of time required for a quantity to double in size or value, and that is approximately related to the exponential growth. We measure this doubling time in terms of this ratio of the logarithmic to the growth rate of the system. So, that gives us an idea about what is the doubling time of the material. If the doubling time is very small, that would mean this material, so it is 70 over r approximately the growth rate. If I know the growth rate, if it is very high, then the doubling time is very small. If the growth rate is low, doubling time is less. So, you have to check the doubling time before selecting the material. And finally, we have to keep this point in mind that certain materials are rarely available, like copper, silver, tungsten, tin and mercury, and iron and aluminum are most widely used. Steel consumption is doubling in every 20 years, it is the material. Aluminum is doubling in every 9 years, even faster, and polymer in every 4 years. So, this sorts of gives us the idea of the materials. And if I get any shortage of a material for my design, then definitely I should go back to the design table. So, my design must be material efficient, use the least amount of material. I have to think of substitution, and I have to think of how to recycle the material. This is where I will put an end in this lecture, and in the next lecture I will talk about furthermore in terms of the use of other things, particularly the property table and the ASPE index. Thank you.